Hey, welcome for those of you joining. This is a completely new topic. We'll be talking about linear regression. Objectives are to describe correlation in terms of strength, linearity, and slope. We'll be solving for correlation coefficients and finding best fitting linear, logarithmic, exponential, and power functions. So a correlation is a measurement of how strongly two variables are related. A strong correlation means that one variable can predict another variable. If there's a positive relationship, then they both happen together. So if there's a positive relationship between hours spent studying and final score, that means the more hours you spend studying, the higher your score would be. If there was a negative relationship, that would mean the more hours you spent studying, the lower your score would be. So whether a correlation is positive or negative is analogous to a slope. So if your slope is positive, as one variable goes up, the other variable goes up. Same thing for the correlation. However, correlation doesn't just have to be for a line. We can use correlation for curves as well. So whether a correlation is positive or negative is the general trend of our data. So we have a couple examples on here. This first one is a pretty much a perfect positive correlation. You can see everything is in a line shape. So I don't have any of my points that are off of the best fitting line. Okay, here's a strong positive correlation. If I was going to create a best fitting line, it might look something like this. Oops, it's a little curved. Okay. So we can still see the general pattern is that as one variable increases, the other variable increases, but there is some error in the points. You can see here. We have some error, or what we would call a residual, is your difference between what actually happened, this point here in blue, and what we expected to happen, which is our best fitting line. The zero correlation means my slope of my best fitting line would be roughly 0. Maximum negative correlation, so just a line going down with all the points on the line. Moderate negative correlation, you can see my points are a little bit more spaced out than they are up here. These points are a little bit closer together. For a stronger correlation, your points will be closer to the actual fitting line. For a weaker correlation, these points will be scattered all over the place. We'll talk about how to calculate what's strong, moderate, or weak later. If you have an outlier, then that does affect your correlations. This is a perfect strong correlation with one outlier. And you can see our correlation coefficient already hit 0.7 from 0.1, so that kind of changed everything. So when we're dealing with correlation, you generally want to get rid of any outliers in your data set before you take your correlation coefficient. Okay, so as far as how to interpret them, generally speaking, if your correlation coefficient is between 0.6 and 1, we call it strong. If it's between 0.4 and 0.6, it's moderate, and if it's from 0.4 or lower, we call it weak. Your correlations coefficients can be negative. In that case, you can just take the absolute value to determine whether this is a strong, moderate, or weak correlation. Later on, I'll be taking this square just to really make sure that it's strong, moderate, or weak. Okay. Key point is that correlation does not prove causation. I think we looked at this earlier in quarter 2. I can't remember, but there's a kind of textbook example of murder and ice cream rates where if you're going to look at my home state, actually, this holds true. So in the state of Florida, at months where there are more ice cream sales, there tend to be more instances of murder. It's not that selling more ice cream causes people to kill other people, or that people are really sad that people are dying because of murder and are buying more ice cream. It's probably something to do with a third outside variable, like temperature, where when it's hotter outside, people tend to be in closer contact with each other and have more opportunities to murder, tend to be a little bit more upset or angry. but also tend to buy ice cream. So just because two variables always happen together, so I can use the ice cream sales to accurately predict murder rates in my state.
Is it possible that the people who sell the ice cream are the murderers?
Uh, it's possible but unlikely. The point here is that just because these two variables happen together doesn't mean that one causes another thing to happen.
Oh, okay.
Okay, so we're going to be finding best fitting lines. Um, in the past in Algebra 2, actually way before that, so as early as grade 6 in our school, they were connecting 2 points and creating a line that generally talk about data. We're going to do a little bit more of an involved technique here, looking at standard deviations and the averages, and kind of using those to create a best fitting line that is as close as possible to all of the points. So our goal here is to minimize the error between every point and our best fitting line. So if I was going to draw in red the distance from every point to the line, if I was going to add up those distances, I would want it to be as small as possible in order to have the best possible best fitting line. We can do this by hand. However, most of you, if you keep going to any kind of science in college or any kind of statistics or science-based profession, are going to use a computer to do this instead. So I'm not going to focus too much on how you do this by hand, but I'm going to show you once just so you can see how it's done. In your homework, you will not have to calculate this by hand. I will let you use a graphing calculator, and I do have a website for those of you that don't have a graphing calculator at home. Okay, so again, our goal is to minimize this R, so our residuals, residual 1, 2, 3, and also to get a correlation coefficient, which can tell us the strength of the relationship between the two variables. So if I can get a line, we'll know the slope. If I can get a correlation coefficient, we'll know how strong the relationship is. So we'll know if it's positive, negative, and strong or weak. And then because we're dealing with a line, we know the relationship will be linear for our estimate. Okay, so we're going to start with y equals mx plus b, where m is, in this case, b1, our slope of the line, and b0 is our y-intercept. I could also say that my slope of the line is equal to my correlation coefficient times the standard deviation of y divided by the standard deviation of x. A slope is change in y over change in x. Our standard deviation is considering that for every single point. So if you had a perfect correlation coefficient, then this would just be 1. And I would be multiplying by the standard deviation of y over the standard deviation of x to get our slope. So you can think of our correlation coefficient as a measure for how wrong our best fitting line's slope is compared to the standard error, the standard deviation of y and x. Okay, so if this y hat is our expected value, then there should be some observed value that we have for each of the points. Since we can't get a perfect line for all of our observed values unless this is a perfectly straight line, I'm going to look at averages instead to give us a basis of comparison. So I'm going to take our average y and our average x and use that to build our slope with our y-intercept. So just draw a line between the average y and x and use that to calculate a line. Okay, so with that, if you were to solve for the slope, I could end up with this. We can check really quick. The slope is a change in y over change in x, gives us a dy over a dx. And I'm summing them all up for every single point in order to get an estimate for our slope. Okay, so here's what it looks like. If I really wanted to do this by hand, so let's say I've got different temperatures here in degrees Fahrenheit and different amounts of water consumption for a household. So I want to see, is the water consumption for my apartment dependent on how hot it is outside? And then what is the relationship? So I'm going to start out by building up to this formula for our slope and getting our standard deviations and averages. So since we've already done this part, get standard deviations and averages before, I'm not going to focus on that too much. If you want to do this through a calculator, you can, and I'll show you how to do that in a second. But I'm going to write down all of my x's and y values in a table. So here I've rearranged all my x's from least to greatest, and then just copied down their water consumptions over here. So I'm going to take the difference from the averages. So my average was 88. So take the difference from all of these averages for every single possible point. Okay, do the same for my y's, multiply the two together, and then get square this first one. So I can divide after I sum up all of these values. My difference in x times difference in y divided by my difference in x squared to get my estimate for the slope. Okay, then I can use our equation for our correlation coefficient using our sample standard deviations. Okay, so I've got my graphing calculator here. Previously, if you hit stat edit, we have built lists before. So I've got all of my temperatures here and all of our water consumption in ounces. So if I hit stat, calculate one variable stats, this should give us our sample standard deviations and our averages for both temperature and water consumption. Okay. So if you wanted to calculate your least squared regression line, so that's your best possible best fitting line with a calculator, we can do what we've just done. So create two lists in your calculator, and then do what's called a linear regression t-test. So in your calculator, if you hit stat and go over to tests and scroll to linear regression t-test, by default, this will take x as list 1 and y as list 2, and hit calculate. Okay, so what this does is this creates a best fitting line for us and gives us our correlation coefficients. So you can see our equation right now is y equals a plus bx. The calculator just assigns variables all the way through the alphabet, a, b, c, d. This is really my y-intercept and my slope, which they gave to us, so I could graph this line if we wanted to. If I did want to graph this line, I guess I'll go ahead and graph now. I can hit y equals and go to variables, statistics, equation, regression equation, and that will paste in the regression equation of the last function that we did. So since the last thing I did was my linear regression t-test, that pastes in the line that we just found, so I don't have to worry about any rounding or anything. I'm also going to go in and graph my points as well. So if you hit second stat plot, under plot 1, I'm going to turn that on. I'm graphing x as list 1 and y as list 2 as a scatter plot. Okay, so I'm going to zoom to my data as well. So if I hit zoom and go down to zoom stat, that will set the window so that I can see all the points. So here's all of the points that was in our data set for temperature and water consumption and our best possible best fitting line. Okay, that was pretty fast. Any questions about what we did so far? We're about halfway through.
Nope.
Wow.
Okay. So our linear regression t-test, if I go back to that, also gave us a p-value, which is a probability. So this p-value is the probability that we would get a score that is that far away from the mean. So it's very similar to what we did with our z-tests in our t-tests from quarter 2, where we've got an average And then we're so many standard deviations away from average when testing for our linear regression t-test. So this gives us a confidence level, really. Our p-value right now is 5.02 times 10 to the negative fourth power, or move the decimal 1, 2, 3, 4 times. So that's 0.0005 is my probability. So as a percent, I'd move the decimal twice, and is about 0.05%, is a chance that I would get a relationship that is this strong randomly. So I could be 99.95% confident that this relationship is not random. This relationship did not occur due to random chance. Looking at my r squared, my r squared is 0.9. That is above the 0.6 that we need. So r squared is greater than 0.6, which means this relationship is a strong relationship. The points are very close to the line. And my r is positive. So I could say I have a strong, positive, linear relationship between temperature and water consumption. And we can be 99.95% confident that it exists. Okay. So that means that with this formula that we've created for our line, we can start predicting water consumption based on the temperature as long as we are within the range of our data set. It is possible to find relationships that don't continue outside of a range. For instance, if I was going to look at age versus height, I might be able to find a strong relationship between your age and your height. If I was looking at people between ages 4 and ages 16. But once I go outside that range, the relationship doesn't continue. We kind of flatline, right? So just because our relationship was true from our lowest temperature to our highest temperature, and our lowest water consumption to our highest water consumption, doesn't mean that it's true outside of that range. So there are some limitations to what we can do with this. We can interpolate data, which means guess new values using our equation within that range, but we cannot extrapolate. Which means guess outside of that range. I don't know if this relationship between temperature and water consumption will hold true if I get down to 60 degrees Fahrenheit. Okay, so dangers, extrapolation, we only predict values within the range of our data set. We can kind of see that there are problems just looking at the formula. Because if I'm below 0, if I am 0 degrees exactly, then this would be negative 96.8 for my water consumption, which means I created 96.8 ounces of water, which doesn't make sense. So this linear relationship isn't true for all temperatures. It's only true for our temperature range. Okay, so now we start to get a little bit more advanced. Instead of getting a best fitting line, I want to get a best fitting curve. So to get a best fitting curve, I'm going to work through 3 different types of transformations that we can do today. So let's say I wanted my best possible exponential function that could fit the data. What I could do is I could take the natural log of all of my y values. So instead of y equals mx plus b, I'm going to take all of our water consumptions and take the natural log of them first before we start graphing. So that means my y value is really the natural log of y. So when you get your equation, this now represents the natural log of y, not just y. Now if I go back to solve for my original y value, I can raise both sides to a base of e, and then use properties of exponents to break this apart. So this would be, to the next line, equals e to the mx times e to the b power. If I'm adding in my exponent, then I'm multiplying with the same base. That e to the b is a constant, so I'm going to call that c because it's not really b anymore. It's e to the b power, but it's still a constant that I can throw on the outside. So now I have an exponential function instead of a linear function, but we can do our linear regression t-test like we would normally if we use our values for the natural log of y. Here's what it looks like. So in my graphing calculator right now, if I go to stat edit, I have list 1 as my x values and list 2 is my y values. I'm going to go over to list 4 because I'm going to use list 3 for my natural log of x values later for a different transformation. So list 4 is going to be the natural log of list 2, which is my y. Okay, so now I've got list 1 is my x values, list 2 is my original y values, and list 4 is my transformed natural log of y. Okay, I'm going to write that down really quick. So this is list 1 right now is x, list 2 right now is y, list 3 we haven't done anything with yet, and list 4 is my natural log of y. Okay, so now if I break out of this and want to do my linear regression t-test, instead of putting list 2 for y, I'm going to put list 4 for y. So I'm using my transformed y values and calculate. We'll get a best fitting linear function to, this says y, but this is actually the natural log of our original y values, was what we used for all of our y values for the calculator. And then we can transform that function back. Now your calculator can do this automatically for you, so I'm going to show you that really quick as well. If you hit stat calculate natural log regression, then this will automatically transform your list 1 as x and your list 2 as y into whatever it needs to do your regression formulas. So this is our best fitting function that would give us a logarithmic relationship to the data. Okay, I'm going to do another one for exponential because we're actually doing exponential right now. So I've got an exponential regression. Gives us a best fitting exponential function to our data. Again, what they're really doing is they're taking the natural log of all your y values, solving for the best fitting line, and then undoing that line because we know that this is really a natural log of y to become an exponential function instead. Okay, if I graph it now, so I'm going to clear out our old best fitting line. So, and I'm going to graph our new regression equation. So this is variables, statistics, equation, regression equation. And it's going to paste the last regression equation we did, which was that exponential function. So if I graph, here's all of our points, and you can see our best fitting function is now a curved exponential function, not just a line. Okay, any questions on what we did? Okay. So what that means is we've got an exponential function that we can use to predict values within our data range. Okay, I'm going to leave this for you guys. These are all of the calculator steps that I just did really fast. So if you want to slow down later and try them on your own, you can. And then we've got two more types of transformations I want to get through today. So logarithmic regression means instead of taking the natural log of y, I would take the natural log of x. So here's my original temperatures. I'm going to take the natural log of all of those temperatures. And then technically this is already a logarithmic function, but I'm going to use power properties of logarithms to move this up to get our equation for the logarithmic curve that we will be creating now. So if I wanted to do this really fast in my calculator, I'm going to hit stat, edit, and then here in list 3, if you scroll up to the name and press enter, you can create a function for it. So my function is going to be the natural log of all of my list 1 values. That'll paste in the natural log of all of my x values for list 3. Okay, if I hit second quit, hit stat, calculate a logarithmic regression function. Okay, this gives me my best fitting logarithmic formula in a logarithmic form. So this is a plus b ln x, where a and b are constants. You can check my r really quick. My r is 0.953. If I wanted to do a linear regression t-test with my transformed function, then instead of x, I would use my list 3, which is the natural log of x. And my y has not changed this time, so that's still list 2. Okay, if I calculate and I did everything correct, then my r should still be the same. And it is. Which means this best fitting line that we just found the probability of getting and the correlation coefficient for actually represents a logarithmic function, not a line. So it's not a straight line, it's a curve. Okay, the probability of getting an logarithmic in this case. The probability of getting a logarithmic function that is this close to all of the points, that is this representative of all of the data, is very small. So you can see the probability of having this happen randomly is not very high. That's 0.0008 or 0.8%. So again, we can be more than 99% confident that we have a strong positive logarithmic relationship to the data set in this case. Okay, if I compare that with what we got last time, my r squared was 0.908. Last time my r squared was 0.964. So this exponential regression function was a better fit to our data than this logarithmic regression function was. So if I wanted to make predictions, I would use our previous exponential regression formula and not our logarithmic regression. Okay, last one. A power regression is what happens when we take the natural log of both x and y. So if I do, I've got a little bit more work to solve for y. So instead of y, in y equals mx plus b form, my y is really the natural log of y. So when I graphed, I didn't graph x versus y, I graphed ln x versus ln y, which changed all of my points. And then we got a new best fitting function to all of those points. Which means my y equals mx plus b for this best fitting line is really ln y equals m ln x plus b, because my y is ln y and my x is ln x. So if I want to untransform this function to get my original y and x, which were curved, then my best fitting line that we created can also be transformed. So I'm going to use power property to move this up. I'll take I'll raise both sides to a base of e, which will get rid of this e and ln e to give me y on the left side. So now I have y equals e raised to the ln x to the m plus b power. With properties of exponents, this plus b can be moved out, so I'm multiplying by e to the b, which is a constant c. E to the ln can also cancel, so that's c times x to the m power, which is a power function, which is another type of curve. Okay, if I do it in the calculator, if I go to stat edit, we already have natural log of x for list 3 and natural log of y from list 4 from when we found logarithmic regression and exponential regression. So I'm going to go over to calculate a power regression function. That'll do our transformation for us automatically that we just did here on our work. Gives us our strength of the correlation and the function that we would need to make predictions. If I wanted to do a linear regression t-test to see how probable it is that this happened randomly, which also gives me an estimate for how confident we can be in our relationship between these two variables, that relationship is a power function relationship. Then instead of doing just my x and y, I'm going to do the natural log of x and the natural log of y, and then calculate that linear regression t-test. My p-value again is small, which means there's not a very high probability that this could happen randomly. So if this is not happening randomly, then there is a relationship between these two variables. So we can be confident that relationship exists, and that relationship is strong. Okay, if I compare it with everything we've done so far, so here's my original best fitting line. Had a strength of 0.92. My logarithmic had a 0.908 strength. My power function had a 0.957 strength. So my highest strength, my strongest relationship to the data was our exponential function. And then if we do our linear regression t-test using our exponential function data, so that's taking the natural log of y, but leaving x alone. Then we can get an estimate for how probable it is that relationship happened randomly. So because it is very not probable, it is not very probable that this relationship could happen randomly, I could say that we are more than 99% confident based on our p-value that there is a strong, because this is 0.96 is above 0.6, positive because our r is positive, exponential because that was our strongest relationship to the data, relationship between temperature and water consumption, which means the hotter it is outside, our water consumption will increase exponentially. And then we can use this function to make predictions for how much water consumption I will need for my apartment based on the temperature outside. Okay, any questions on what we did?
Hmm.
Okay. I do have some practice problems that I've posted to the WeChat and Skype that I'll be taking for homework on Thursday at 9 a.m. If you have questions, please message me on the WeChat. Your test that you guys were taking, if you have not submitted yet, is due today at midnight. I did have a couple people say they were having trouble submitting it on course sites, so if that's you, just send it to me through WeChat. If you did already send it to me through WeChat, I should have you already, so I'll send you messages just confirming that in a minute. Okay, thank you guys for coming.
Thank you.